Hello everybody. What I'm going to do now is give an introduction, a very, very basic introduction to circuits. Very basic, just having a battery and a wire and some resistors. Okay, so first thing to know are the symbols. So here are the symbols that we've got. As you can see, we have the battery, right? And the battery is just a line with a long line and a short line, and then the wire continues. A switch looks like this because you can open and close the switch. A resistor is this zigzag line, and the bulb, a resistor could be a bulb. You know, a bulb could be one of the things in the circuit that's providing some resistance. But if it's a bulb and you want to make it specific that it's a bulb, then you can use this symbol for a bulb, or you could use a resistor. Either way. When you're measuring voltage or you're measuring current, then you're using a voltmeter or an ammeter. Ammeter because you're measuring amps. Amps are the unit for current, which we'll get to in a second. So the way that you indicate that in a circuit diagram is a wire with a V or the wire with an A for voltmeter or ammeter. Next thing we need to know are the quantities. What is it that we're measuring? What is it that we are calculating? So first of all, voltage. Voltage is abbreviated with a V, and the units, volts, are also abbreviated with a capital V. It's maybe the only time where the quantity and the units are both the same letter, voltage and volts. Another word for potential, by the way, or voltage could be potential. You hear electric potential. And then as you get more advanced in circuits, you might hear about EMF, electromotive force. It's all referring roughly to this same idea, potential difference or voltage. Current is abbreviated with an I, which seems strange. Why would current? What does I have to do with current? Well, here's a little background on it. Current used to be called current intensity, and so intensity comes from the I. Any old textbooks, old physics textbooks, you'll see current referred to as current intensity. Over time, we got lazy and we dropped intensity, so now it's just called current. In French, it's intensité de courant. Right? In French, you can say ha 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 when you're done saying that. But the I comes first. So the I, intensity of current, or current intensity, that's where the I comes from as the abbreviation for current. Capital I is what we usually use. If you're into advanced circuits and you have variable current, we use a lowercase I traditionally. That's measured in amps, short for ampere, the scientist. Okay. And then resistance. Resistance is the, resisting a current. We abbreviate that with an R, and it's measured in ohms. Ohms, the abbreviation is a capital Greek letter omega. Looks like an upside down horseshoe. Power. This is the same kind of power that you learned about in energy, work, energy, and power. And it's measured in watts. Same way that you measured it way back when. Okay. So, next thing to do, now we're going to look at the basic equations. There are two basic equations here, and there's a way of arranging quantities in a table that kind of helps to organize it. So here they are. The first basic equation, you can call this the man equation because vir, V-I-R, is the Latin word for man. So V-I-R, V equals I-R. That means that the voltage equals the current times the resistance. Another way of writing this that might be helpful is that current is a result of V over R. That's kind of the causal version of the equation. How do we get current? Well, we have a potential difference, and then the amount of current will be determined by how much potential there is and how much resistance there is. So potential and resistance are the cause of current. And then another important equation, P equals IV. Power equals the voltage times the current. And if you have to, you can substitute either of those things in there, right? Like for V, you could substitute IR, so P equals I squared R, a bunch of different substitutions. Now, if we arrange these quantities in this order, RIVP, then you can see it's in order of how we multiply things. R times I equals V, and I times V equals P. So that's the RIVPA way of arranging the quantities. If you have a table, you can arrange it that way, and it's easy just to multiply across or divide and know what you have to do to get from one column to the other. here's a very, very simple, very basic example of a circuit and a question that you might see. It's just one battery, one bulb, as you can see in the diagram. And the question is, what's the current flowing through this circuit? Well, first of all, current always flows from positive to negative. It's actually opposite the direction of the flow of electrons. I'm not even sure I should tell you that. Don't want to confuse you. But because electrons are negative, it's opposite. So anyway, the positive side of the battery is the long line, and the negative side of the battery is the short line. So the current is flowing in this direction, clockwise around this circuit. Okay, and we're looking for the current, right? So V equals IR, that's what we're going to use. I equals V over R. So this is really simple. V, 9 volts, the resistance, 3 ohms, and that gives us a current of 3 amps. Amps are the unit for current. Okay, now I'm going to give you a couple of analogies for thinking about circuits. When you get to things that are a little more advanced, it's good to think in terms of analogies because this can feel really abstract. We're not seeing the current that's moving. And so a couple of analogies where we actually kind of do see the current. One would be the analogy of a track. If we have a line of runners on a track, then in that case, the runners themselves are the current as they're going around the track. The battery would be a couple of things. This is where I don't think this analogy works too well for this particular thing, but it could be the coach, or it could be the food that the runners ate. And the food is giving the runners energy to go around the track, because the battery gives a potential difference to create an electric field and push the charged particles through the circuit. Or maybe it's the coach. You can see the coach there with the megaphone pushing the runners along the track. The resistor would be something like a hurdle. If we put some hurdles on the track, then that's going to slow them down a little bit. So the resistor, for this analogy, is the hurdles that we put on the track. So the more hurdles that we put on the track, the more it slows them down. So that's like putting more resistors into a circuit. You're going to get less current by doing that. Right. Okay. Another analogy would be a waterfall. The current would be just the water itself. That's pretty simple. Okay. And then the battery would be a pump. So if you imagine a water pump, the pump is, with a real waterfall, pumping the water up, giving that water gravitational potential energy. Well, that's pretty much what the battery is doing, except that instead of gravitational potential energy, it's electrical potential energy. So each particle is given electrical potential energy, and it's pushed along the circuit. Okay, and then as the water goes along, it's going to fall. And as it falls, it's using up energy. And then that energy could be used to do something, like to power a water wheel. And then that's like in the circuit, those drops of potential, that's what happens across a resistor or a bulb or a little electric motor or something like that. So the resistor is the waterfall as the water comes down. So that is all together very, very basic circuit overview. So thanks for watching. Don't forget to like and subscribe.